You're listening to the National Media Archive. To learn more or volunteer, go to nationalmediaarchive.com. Imagine you're out on a long, quiet drive, wheels humming against the road, when your stomach suddenly lets out a low, impatient grumble. You look around and spot a neon sign promising burgers, fries, maybe a milkshake if you feel generous with your appetite. So you pull in, order a hot dog and a hamburger at the drive-thru, and within moments, two nearly identical cardboard boxes appear at the window, stacked in a bag beside your seat. No labels, no hints, just warm, folded secrets waiting inside. You don't know which box holds the hot dog and which hides the burger, but you do know this. The second you crack open one box and see that juicy burger, you'll instantly know the other box holds the hot dog. They're connected by your knowledge alone, linked by that simple, invisible thread. This small drive-thru moment is, in its own way, a tiny glimpse into the strange dance of quantum entanglement. This curious idea is built on a foundation that begins with the basics of quantum mechanics. But before we leap into the rabbit hole, it helps to remember where we started. Classical mechanics. For centuries, we trusted it to explain the motion of planets, the arc of a thrown ball, the swing of a pendulum. Sir Isaac Newton gave us the rules that made sense of it all. But those rules, as ironclad as they seemed, start to crack when things get unimaginably small. Ask yourself, do atoms and their tiny inhabitants obey the same laws that keep the moon circling Earth? Not quite. Once we zoom down to the realm of electrons and photons, the tiny packets of light that let you see these words, Newton's rules shatter. Here, quantum mechanics takes the wheel, and once it does, reality bends in ways that defy our everyday logic. Let's talk scale for a second. A photon is so small it slips through most things unnoticed. An electron is so tiny that billions of them could perch comfortably on the sharp tip of a sewing needle. It's easy to forget these tiny beings are the real architects of our universe, holding everything together while living in a world that looks nothing like ours. Now, picture this. If you bump into a stranger on the street and they ask, "Who are you?" you'd probably say your name. Maybe you'd throw in where you're from. Simple. But what if a raccoon from another star system walking upright with a cosmic grin asked you the same question? You might say, "I'm Peter Quill, human from Earth." Suddenly, you're layering information, your name, your species, your planet, because that's how identity works when you zoom out. In physics, location is its own kind of identity. An object's spot in our familiar three-dimensional world is locked in by its x, y, and z coordinates. Add time as a fourth dimension, and you get a snapshot of that object's exact where and when. For electrons, though, things get trickier. They live by four special coordinates, four quantum numbers that pin down who they are in the swirling chaos inside an atom. Each electron carries its own passport, principal quantum number, orbital angular momentum quantum number, magnetic quantum number, and finally the electron spin quantum number. No two electrons in the same atom share the exact same four stamps. This cosmic rulebook keeps them in line, defining where they belong in the invisible architecture of matter. Today, though, we'll focus on just one of these strange identity markers, the spin. When physicists talk about an electron's spin, they don't mean it's twirling like a planet or spinning like a dancer. Spin is more abstract, an intrinsic, built-in swirl of angular momentum that gives the electron a magnetic personality. And here's where it gets beautifully weird. An electron doesn't have to pick a spin right away. In its natural state, it exists as both spin up and spin down, simultaneously. This split identity is called superposition. It's like flipping a coin and watching it hover in the air, forever spinning, never landing. Both heads and tails exist at once, until you catch it and peek at the result. The moment you measure it, reality picks a side. Physicists call this the collapse of the wave function. Before you look, possibility reigns. After you look, certainty snaps shut like that burger box in your car. This same unsettling idea inspired one of the most famous thought experiments in science, Schrödinger's cat. Imagine a sealed box with a living cat inside, a speck of radioactive material, a fragile vial of poison, and a Geiger counter rigged to smash the vial if the radioactive material decays. The twist? You can't know if the material has decayed until you open the box. So until that lid lifts, the cat hovers in a ghostly state, alive and dead at once. A tragic, ridiculous paradox that captures the heart of superposition. In the quantum world, this double life isn't just philosophical poetry, it's real. Electrons stay suspended in their both-ways state until something, anything, forces them to decide, and sometimes that decision echoes across the universe in a heartbeat. This brings us back to quantum entanglement, where two electrons become linked like secret twins. If they share a moment in space, born together, touched together, they become entangled. After that, they never truly separate. One can drift far from the other, across a lab, across continents, even galaxies. Yet when you measure one electron's spin, the other's spin collapses in perfect opposition, instantly. If you find spin up here, you get spin down there, no matter how impossibly far there might be. This instant connection puzzled and infuriated Albert Einstein. He dismissed it as spooky action at a distance, a phrase that lingers because it perfectly captures the unsettling nature of what's happening. How can information leap across the universe faster than light? How does one electron know what its twin has revealed? So what can we do with this eerie trick of nature? Turns out quite a lot, if we can tame it. Entangled particles might sound like the stuff of sci-fi bedtime stories, but their strangeness could help us keep our world ticking in surprising ways. Take clocks, for example. Modern life runs on time, stock exchanges, data transfers, navigation, the heartbeat of cities. Atomic clocks, like the quantum logic clock at the National Institute of Standards and Technology in Colorado, already keep time so precise they drift by less than a second over the entire age of the universe, 33 billion years and counting. But even these clocks rely on local signals, tiny, isolated pulses that can slip or slide ever so slightly out of sync. Entangled clocks, on the other hand, could bind these signals together. By weaving atoms into an entangled state, scientists imagine a worldwide network of perfectly coordinated ticks and tocks. More atoms mean more precision. If one clock drifts, its entangled siblings tug it gently back into line. A single pendulum swinging everywhere at once, independent of where you stand on Earth. The benefits ripple outward. More accurate clocks mean sharper GPS systems, more dependable data networks, financial trades that execute with an edge of certainty. It's a step toward a world that runs in perfect time, everywhere. Then there's security. Think back to the secret codes you and your best friend scribbled in class. Those whispered alphabets, clever substitutions, the thrill of knowing only the two of you could read them. Quantum cryptography is the grown-up version of that playground magic, only the stakes are much higher and the locks far stronger. Here, entangled particles, tiny photons for instance, carry the keys to decode secret messages. If anyone tries to snoop, the entanglement shatters and the intrusion is obvious. No hacking, no guessing the password, just a silent alarm hardwired into the physics itself. This isn't a far-off fantasy. In 2007, Switzerland dipped its toe into quantum cryptography during an election, testing a secure voting system that used quantum key distribution. The idea is simple but powerful. If you entangle the keys, any tampering becomes immediately clear. It's a new breed of honesty, built right into the fabric of communication. But the quantum toolkit doesn't stop there. Researchers in Japan at Hokkaido University took the idea even further, building the first entanglement-enhanced microscope. Using entangled photons, they unlocked a deeper layer of information, peering into the living world with more clarity than traditional light could muster. Measure one photon and you learn about its twin, distant but inseparable, like reading two books by opening one cover. And then, of course, there's the whispered dream of teleportation. Science fiction loves to imagine humans stepping into a shimmering beam, reassembling atom by atom somewhere else. Quantum teleportation is not that. In reality, it's subtler. No people dissolving into light, no spaceships beaming up lost adventurers. Here, teleportation means transferring information. One particle's identity is instantaneously transferred to another, destroying the original in the process. No atoms travel, just the blueprint. A delicate promise that one day, secure communication could leapfrog the old wires and satellites we rely on now. All of this, atomic clocks ticking together, secret messages guarded by the universe's own rules, particles whispering secrets across space, is only the beginning. Quantum entanglement is still more question than answer, more mystery than certainty. Yet every experiment brings us a little closer to wielding it, folding the weirdness of the quantum world into our daily lives. And beneath all these breakthroughs is the same slippery truth. The quantum realm doesn't obey the logic that makes our coffee drip or our cars roll down the highway. It follows its own script, one we're still struggling to read. It asks us to accept that particles can be here and there, alive and dead, spinning up and spinning down, until we peek inside the box. Richard Feynman, a Nobel laureate and one of quantum theory's best storytellers, said it best. If you think you understand quantum mechanics, you don't understand quantum mechanics. Maybe that's the point. The universe is stranger than we can grasp, yet more precise than we can imagine. And somewhere between the hot dog and the hamburger, the clock and the cat, lies a reality we're only just beginning to taste. So here we are, left staring into the murky, glittering depths of quantum entanglement, trying to make sense of something that refuses to sit still for us. The more we prod at it, the more it reveals its slippery truths that break our tidy categories of near and far, here and there, now and then. This is a world where information ignores distance, where two particles light years apart can still share a secret handshake instantaneously. Physicists push deeper every day. They set up elaborate experiments in darkened labs, lasers, crystal lattices, carefully chilled chambers where particles dance in entangled pairs under watchful eyes. Each test, each entangled photon nudges us a step closer to pulling this spooky action into something we can actually use. But the practical power is only half the allure. What quantum entanglement really does is force us to ask questions about what reality is made of. What does it mean that an electron doesn't choose a spin until we look at it? What does it say about us, the observers, that we shape the truth simply by measuring it? In this strange corner of physics, the boundary between what is and what we know is blurry, perhaps even illusory. So we turn back to our everyday world, fast food wrappers on the clicking on the wall, a text message pinging across continents. All of these things hum along oblivious to the quantum churn below them, yet they depend on it, ride its currents, run on the rules laid down by particles too small for our eyes to see and too weird for our common sense to cage. If quantum entanglement lives up to its promise, tomorrow's technology might not just be faster or smaller, it might be stranger. Ultra-secure data that nobody can intercept without getting caught. Supercharged sensors and telescopes that peer deeper than any lens before. Global networks of atomic clocks that tick together with impossible harmony. Maybe even quantum computers that crack problems so vast they'd make today's fastest machines feel like abacuses. And maybe, just maybe, this will push us to accept that certainty is overrated. That sometimes the only way to get closer to truth is to accept the blurry edge, the probabilities, the unopened box. We build equations, we invent metaphors, cats, coins, tangled particles, to wrestle with the parts of nature that don't bend easily to language. In the end, it's humbling. We are observers in a universe that doesn't much care whether we understand it. But we keep trying. We open boxes, we peer at needles full of electrons, we line up particles and dare them to whisper secrets across billions of miles. If you feel your brain knotting at the thought, good, you're not alone. Feynman would grin that crooked grin and remind you, if you think you understand quantum mechanics, you don't. And maybe that's the beauty of it. Between the hot dog and the hamburger, the cat both breathing and not, the entangled electrons twinned across the cosmos, somewhere in all that impossibility we find the next question worth asking. And then we ask again.